我们上一周应该是讲到这边，就是有提到说，K-means 这个方法，它有可能最终会卡在一个local optima。那我们接下来看，可以怎么去遇到这个问题怎么办？这样子 ，OK。Okay, so how we could solve the problem of local optima? So we can say that we decide to run k-means like 100 times. So we will run this loop 100 times, and it's a typical a number of times when come to uh, like something from five 500 up to maybe 1,000. Okay, so let's say we decide to um, to say k means 100 times. So what the means sorry. So what that means is that we would randomly initialize k means. So for each of these hundreds random initialization, we would run k-means, and that would give us a set of clustering like from C1 to Cm, and a set of cluster centroid from mu1 to mu k. So it means we have k cluster centroids and m clustering, and then we would compute the cost of the k means. So this is a cost function on the set of clustering cluster assignment and the cluster centroid that we got. But here I don't prepare to introduce a cost function because this is not the main point of this class. But the same concept have been introduced in the lessons like word embedding. So you can imagine that you have to minimize the output and the some targets. So the cost function is to minimize. The target we have to minimize. So finally we done this whole procedure like 100 times. Then we will have 100 different ways of clustering the data. And then finally, what we did is all these hundreds way we have found of clustering the data, and we just pick one that gives us the lowest cost. And it means that if we run k-means with a small number of clusters, so we know if the number of clusters is from to maybe 10, then doing multiple random initialization can make sure that we find a better local optima, and make sure we find the better clustering data. But the question is, if k is k is means the number of clusters. So if k is very large, it like greater than 10, and if we are trying to find hundreds of clusters, then we have multiple random initialization is less likely to make a huge difference, and there is much uh, higher chance that we uh, we first random initialization give us a pretty decent solution already. So if we do multiple random initialization, we'll probably get a slightly better solution. Okay, but maybe that much. So uh, uh, but it is uh, um, a better way to choose the um, to avoid the local minima and uh, get a better result. So that k-means with random initialization. If we trying to find a cluster with a relatively small number of cluster, we can run multiple times of random initialization that may help us to find much better clustering of data. Okay, and here is another question we haven't talked about is about choosing the number of cluster. And um, one method that we talk about is called elbow method. So what is elbow method? We are going to do is a test vary k and which is the total number of cluster, and we are going to run k-means with one cluster and to uh, the the maximum that we set. So for example, we run we choose k equal to 1 to k equal to 8. So if we choose k equal to 1, that means everything get grouped into a single cluster, and we can compute the cost. So we plot the cost of when we choose k equal to 1. And then we going to and we are going to run k-means with two clusters. So here is k equals 2, and we get the cost about when we choose k equal to 2. Then we run multiple random initialization, and okay, so we get this cost, and then we can go on to test like k equal to equal 3, 4, 5, 6, 7, 8, and so on. And so we end up with the curve showing how the distortion we like go down as we increase number of cluster, and we will get a curve that maybe look like this. So if we look at this curve, it's look like um, a human's arm, right? For example, you can imagine that here is our hand, okay, and this is our shoulder. So it is here is an elbow, and you can call this as elbow method. And in this case, maybe using three cluster is the right number of the k, because the elbow of this curve, right? This is that is go downs and rapidly until k equal 3s, and then it goes down very slow after that. So in this case, we will choose k equal 3. And if you look at this case, the curve looks much more ambiguous. And in this case, there's no clear elbow, but it look like it still it still go down. Maybe 3 is a good number too, but maybe 4 is a better number. Or you can say we have to choose k equals 5. So it is not clear where the good location of the elbow is. So it's harder to choose a number of cluster using elbow method. So um, here is the case of the elbow method that is worth the shot. But it have a very high expectation of it's working for any particular problem. And finally, here's other way to think about how we choose the value of k. It You can choose uh, the k um, uh, running k-means in order to get cluster from some purpose, and especially for your downstream purpose. For example, uh, we if we want to use k-means to do market segmentation, like uh, you want to decide uh, each size of t-shirt you want to make and you will compute that, like the size of S would be much more customer like to uh, buy the size of X size of S t-shirts, and the size of L t-shirt uh, would not be favorable for your customers. So you can uh, based on your purpose to set the value of k based on your uh, your goal. So uh, if it's if we have an evaluation matrix, a better way to determine the number of clusters is to evaluate how well different number of cluster serve the downstream purpose. 好的，那这边就是只是讲到，就是我们有提到在 K-means 中有一个很重要的点是，我们要怎么选要几群，然后当然有一些方法在说我们怎么选要怎么设定这个 K， 也就是选择要分几个群，然后其中一个有蛮直觉的方式就是 elbow method， 就是我们可以 run 很多次 K。从小到大，然后我们可以找一个有一个急速下降的点，然后可能在这边很骤停的感觉，然后接下来下降就变得很缓慢。那这边这个数值代表的是这个 cost function， 可能你有一些可以evaluate 的目标，然后可以去算它的 cost。那如果说它到某个位置下降的比较缓慢之后，我们可以选择也许3。在这个例子3会是一个好的 K 的选择，代表说，在这个资料里面，它分3群是蛮合理的。然后剩下的你可能会问说，那分4为什么不好？那可能它或许在分出第4群的这种感觉的时候，它就比较没那么3来的那么具体的感觉。那这个是算是整个资料集所具有的一种特点，它可以分3群是最具体最好的。然后但是这种方法可能还有一个问题是，如果我们今天得到的结果是一个平滑下降的这个 曲线的话，我们就没有这种很明显的点可以挑，就是这个做法的一个缺陷。那所以另外还有一种讲法是说，我们根据我们的目标来选择说，要分多少个群，然后那这个目标就是看我们想要做什么事情。那这个是可能会包含一些我们对于这个资料集所具备的一些现有的知识或是相关的经验，这样子。好，那接下来就是讲到另外一个部分，因为我们前面是讲这个clustering，然后接下来是讲dimension reduction。那这两个部分主要就是延续前面我们有介绍到word embedding、sense embedding，然后它其实都算是对我们来说它是一个蛮高维度的这种资料。那我们要怎么去对这个资料做一些分析？所以前面有介绍到做 clustering，我们就可以，比如说以 word embedding 来介绍，我们可以把字分群。然后那接下来我们要介绍这个 dimension reduction 是为了这个可视化，就是资料的可视化。好，那我们就往下继续讲。Okay, so in the following slide, I want to talk about the second type of supervised learning problem called dimensionality reduction. There are several different reasons about why we want to do a dimensionality reduction. The one reason is to perform data compression, and it is often the case that we have a vector in we have vectors in very high dimension, and for a lot of machine learning application, it is really helpful to perform dimensionality reduction for developing an effective learning algorithm. If we know about our data better, so one reason is to conduct data compression to make sure we understand the feature our data. Okay, and but here I want to focus on the motivation of dimensionality reduction is to visualize high dimensional data, especially we will talk about word embeddings. So you may want to find a way to reduce the dimension of this vector, like 300 dimensional vector to 2 dimension, and then we can plot the vector of into plot the vector on an XY axis, and we can visualize the word embeddings. So for the problem of dimensionality reduction, one of popular algorithm is called principal component analysis, or we can call it PCA. PCA is an algorithm used for dimensionality reduction that can find one correlative features of your for your data. So it is a helpful method for visualizing our data to check if the representation, okay, the representation like word representation is capturing the relationship amongst words. Okay, here is like the first first word, second words embedding, third word embedding, then we want to reduce the uh, word dimension, word vector dimension, like from 300 to 2, then we can visualize it. So let's see the intuition and the motivation for visualizing word vector or vector representation of words. Um, Imagine we have the following representation for our word in a vector space. And in this case, our vector space dimension is higher than 2. So in this case, the word apple and orange are fruit, so they are related. Then cat and dog are animals, so they are related. And jump and run are related since they represent action. So um, uh, we want to see if the relationship is captured by a representation of our words. So um, how could we visualize our word in order to see uh, this relation and um, other possible relationship? So uh, the answer is to perform dimensionality reduction. We can use this for this task. 好，前面提到就是我所讲的，我们想要把这个你可以想象，就是每一个 row 它都是对应一个 word 的 vector，然后它可能比如说300维的，像我们最常劝 word embedding 把它劝成300维的。然后那这边补充一点，过去有蛮多人做研究，他会测什么从100维、200维一直到1000维。然后有趣的点是300维似乎是在大多的任务中算是表现最偏，就是在比较多的任务中是表现比较好的，所以我们通常会 train 一个300维的 word embedding。但300维对我们来说还是很抽象，我们很难去对它做任何视觉化，所以我们就会想要用一种降维的方式，比如说这边讲到 PCA， 但降维的方式当然还有很多，不止 PCA。那这边就是先介绍一个比较简单的概念，然后我们把它降成2维，我们就可以看它的这个点的分布。点的分布就表示说是字的分布，然后跟前面的概念很像是，如果它是群聚在一起的，或许我们就可以说它们有某种关系。好，然后那刚刚有提到是假设我们今天有这些资料，如果我们这边有一些水果，有一些动物，还有一些动作，然后我们已经知道嘛，水果它应该要是有相似的关联，因为它们都是各种水果，然后可能有一些具有同样的特性，比如它们是可食用等等的。然后再来是动物，那猫狗它可能是有一些特性，比如说它们是哺乳类，可能它们是可饲养的动物等等的属性。那你会预设说，它们也是相似的。那它们动物会彼此应该要因为相似应该要群聚在一起。那跟水果可能就没有太大关联，所以它们应该不会群聚在一起。那再来就是jump 跟 run 是动作，那它们也有相同的属性，那是应该是要群聚在一起，然后跟其他的或许有一些距离这样子。好，那接下来就来介绍可以怎么用 PCA 帮我们做这件事情。Okay, so when we have a representation of our word in a high dimensional space, we could use an algorithm like PCA to get a representation on a vector space with fewer dimension, like d equals 2. And so if we want to visualize our data, we can get a reduced representation with fewer features. So, for example, if we perform principal component analysis on our data, and the data is means sorry, data means um, word vectors, and we get a two-dimensional representation, then we can plot uh, a visual of our words. So in this case, we might find that our initial representation captured the relationship between the words apple and orange and bananas in they are related, and dog, wolf, lion, cat are related, and uh, jump, run, fly, walk are related. And because in our two-dimensional space, they appear to be a cluster with the related word. So we can even find other relationship among our words that we didn't expect it, like um, this is much more abstract, and these words are much more concrete. So you can see these two clusters are closer each other, and there is a space between uh, the cluster that contains the word about verb or action. So it is fun and useful possibility. So let's see the PCA problem formulation. Suppose we have a data set that these we have 5 points of data, and let's say we want to reduce uh, the dimension of the data from two dimensional to one dimensional. So in other words, we would like to find a line and project the data onto this line. So what seems like a good line onto uh, which to project the data is it's the line like this. Uh, might be a pretty good choice, because if you look at uh, where the project version of the point scale, uh, like we can take this point and project down here, and this point project down here, and this data is project down here, here, and we find it's that the distance between each point and the the projection, the point project on this line is here. um, you can see the distance is the blue line is pretty small, is pretty short. So um, what PCA does formally is to try to find a lower dimensional surface. In this case, is a line, and uh, we find a lower dimensional surface onto which to project the data. So a project the data so that the sum of square of this uh, blue line is minimized, and the length of those blue lines um, is called projection arrow. So what PCA does is to try to find the surface um, that we can uh, project data, so to minimize it. 那所以简单来说，PCA 要做的事情就是找这个，把它降到一个，我们想要找一个 surface。那这个 surface 如果我们原本 data 是2维，它就是找1维；如果是3维，就是找2维。然后，我们想要把它投射到这个 surface 上面，然后目标是希望这个，呃，投射到这个 surface 上面的这个距离，这个蓝色的距离可以越小越好。So here's another example. In contrast to the red light in the previous slide, here is a different light onto which we could project our data. So it is this line, and we can see this line is much worse than the previous than the line in the previous slides, right? If we project our data onto this line, we we can also get a set of points like this, and the projection arrow is the blue line will be huge. So this point have to move a huge distance in order to get uh, onto this line. So the PCA will choose like the red line in the previous slides rather than this line. 好，那这个是相较于前面的例子，它是一个比较不好的选择，就是大家可以看到这个projection error 比较长、比较大，就是它这个点要走比较远才可以到这个 surface 上。好，那所以重点就是在于说选择一条，如果是这样的情况，就是要选择一条线，那可以让这个projection error 越小越好。So we can write the PCA problem a little more formally. So we can say the goal of PCA, uh, like if we want to reduce the data from 2-dimensional to 1-dimensional, we are going to find a vector like u1. Uh, uh, so like here is Rn means we want to um, find R2. So we gonna find the direction onto which to project the data to minimize the projection error. So in this example, we are hoping that PCA will find this line. So it's called U1, and um, in this case, we will end up with a pretty small reconstruction error. And in, you may ask that minus U1 is okay. The answer is it is doesn't matter. You can say you find a vector is minus mu1 minus U1. It's uh, it is okay. It's fine. And so um, in other words, it's give a possible a positive u1 or a negative u1. It doesn't matter because each of these vector define the same red line. Then that makes our projection error can be minimized. So in this case, re, uh, reducing data from two-dimensional to one-dimensional, if But in more general case, we have like more like n-dimensional data, and we want to reduce to k-dimensional. So we want to find not just a single vector to project the data. We want to find k dimension onto which to project the data. And the goal is to minimize the projection error. So for example, if we have 3D data like this, and we say that the PCA problem is to find a surface. So in this case, to find a 2D surface, and we can project the data onto this surface. So it is a 2D surface. Then this is a 2D surface which we are going to project our data. So for uh, um, for we're gonna find um, a set of vector u1 and u2 to represent this surface, or if you want to find a k dimension surface, then it might be you may be up to mu k, and uh, so finding a k-dimensional surface is really uh, like finding a 2D surface in this case, like in these figures. And we can define the position of the point in the plane like using k direction. And the reason for that's why for PCA we want to find k vector onto which to project the data. So in PCA we want to do is to find the way to project the data to minimize the projection distance, uh, which is the distance between the point and the projection. OK，那如果就是相较于前面是二维的，我们现在是三维的资料，那就是可以想象成是要把这些三维空间的点，把它去投射到这个二维的平面，然后它们的这个距离，这个点到这个平面的距离是越小越好的。那这边下面接下来就是很快的跟大家介绍这个关于PCA 的一些这个正正式的一些怎么讲演算法的过程，但是这个就是大家大概知道就可以。OK， 好，so now we know what PCA can help us. Let's dive into detail how it works. So at first we find a set of uncorrelated features and then project our data to one-dimensional space uh, to retain as much information as possible. So as you can see, the process is easily understand. Like you will see the details, how to get uncorrelated features, and we will also project our data for representation any lower dimension, but it still retain as much information as possible. So how can we reduce the dimension of our data? Before applying PCA, there is a data preprocessing step we can do given the set of example, and then depending on our data, um, uh, this is very similar to find uh, uh, the mean normalization and feature scaling process that uh, 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 is one of important step in PCA, and um, in fact it is exactly the same procedure expect that we are doing now to our unlabeled data from X1 through uh, 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 XM. Sorry, here's a typo. This is XM from X1 to XM. Okay. So for uh, mean normalization, we first compute the mean of each features, and then we replace each features X uh, um, with X minus its mean. And so this makes each feature have exactly zero mean. And note that the difference feature have very different scale. So for instance, if X1 is like size of house and X2 is the number of rooms, we then also scale each feature to have a comparable range of value. And similar to what we have, uh, uh, we would take uh, x I x super I sub j, that the j feature of uh, xij. So we would subtract of the mean mu j, and then divide by sj. So we would so here sj measure the uh, value of uh, feature j. So it could be the max minimum value, or uh, you can call it a standard deviation of feature j. 好，那这边的过程就是，我们会先对这个m 这边写错，这边是 x，就是我们有 m 个没有标记的，就是我们不知道它是属于什么样的类别的资料，然后我们先对它做 mean normalization，然后也还可以做 feature scaling，就是根据我们的数据来决定的。然后那总之就是做 mean normalization，我们去首先要先计算出mu，然后我们用x 减 mu 来替换掉 x，就是让所有特征的 mean 都是0，然后那做法就是像是 xij 减掉平均值，然后再除以这个 sj 来替换掉 d 这个特征，然后用这边的 sj 是这个 d 这个特征的一个的某个范围，然后它可以用来表示像是最大值减最小值等等的。那我们也可以说它是表示这个 d 这个特征的标准差。Okay, so having done this sort of data preprocessing, here are what PCA algorithm does. So we saw from the previous slide, it tried to find a lower dimensional subspace into which to project the data so as to minimize the square projection errors. So we sum of square projection arrow as the square of the length of those blue lines. So what we want to do specifically is to find the vector u1 and or a 2D vector u1 and u2 to define this surface. So just here's a quick remember of what reducing the dimension of data means. Uh, uh, in a lab example, we were given the example of x1, x2, and we like to find the number of z1 in here to represent our data x1. We want to find the number z2 to represent our data x2. So it is the process of reducing from 2D to 1D. So specifically by projecting data onto this line here. And we here we only need one number to specify the position of the data. So we can call the number as z or z1. Here z is a real number. Okay, so so here x1 map to z1, x2 map to z2, x3 z2 map to z3, and so on. So what PCA has to do is we need to come up with a way to compute two things. One thing is this vector u1, or in this case is u1 and u2, and the other thing is how do we compute this number z, or the vector z. So how do we compute all these quantities? Uh, the mathematical proof is complicated, and we will not talk about the mathematical proof in the following. We will just discussing the basic concept of PCA procedure. 好，那我们目前大概知道说要做什么事情，只是还有一些不知道怎么算的，像是我们怎么计算出 U1 或是 U1 U2，然后还有怎么计算出 Z 这些数值。那等一下我们可以来看一下这些是怎么做的。好，那刚好到下课时间，我们就先休息一下，休息10分钟，我们再来讲后面的内容。 好，那我们再来上课。Okay, let's see the procedure of PCA algorithm. Let's say we want to reduce the data from n dimensions to k dimensions. And what we're going to do is first compute covariance matrix, 共变异数矩阵. And the covariance matrix is commonly denoted by these Greek alphabet is called sigma. And it is a little uh, uh, confused that uh, this is also look like the uh, alphabet of covariance matrix. Um, they looks exactly like the Greek alphabet sigma looks exactly like um, the summation symbol. Uh, but remember, uh, the Greek alphabet sigma is used to um, denote the matrix, and this is a summation symbol. So this is covariance matrix, and this is summation symbol. Okay, how do we compute this matrix? What we need to do is to compute uh, something like uh, uh, it is called eigenvector of matrix sigma. So formally, um, we can use like this comment and u sv equal svd of sigma. So here svd is singular value decomposition. We can use to it to compute the matrix u s and d of covariance matrix sigma. So just to fill in some more details, um, this covariance matrix sigma will be uh, uh, n by n matrix, and one way to see that is if we look at the definition, uh, it is n by 1 vector, and this is uh, uh, a transpose matrix, so it is 1 by n. So the product of these two matrix is going to be uh, an n by n matrix. And what the singular value decomposition output 3 u s and v, the thing we really need the svd is the u matrix, the and u matrix will also be an n by n matrix. So to perform dimensionality reduction using PCA, beginning with our original vector, we get uncorrelated feature for our data, and finally we project our data to a number of desired feature that retain the most information. And you may recall that the matrix has eigenvector and eigenvalue, but here it is not the main point how to get those right now, but um, uh, it is useful because of because the eigenvector of covariance matrix from our data, and we give direction of uncorrelated feature and the eigenvalue are the variance of our data set in each of these new features. So to perform PCA, we will need to get eigenvector and eigenvalue from the covariance matrix of our data. So to sum up eigenvector from covariance matrix of our normalized data, give the direction of uncorrelated features and eigenvalue associated with these eigenvectors tell us the variance of our data on those features. So it's the product between our like word embedding and a matrix of eigenvector will project our data onto a new vector space of dimension that we choose. 那 PCA 会跟一个概念很相似，是我们会用到奇异值分解，但是这边我们没有想要很深入的讲这一点，这个就是线性代数的部分这样子。那总之就是我们会用到 eigenvector eigenvalue 的概念，然后用来帮助我们去决定这个怎么去这个做这个降维这样子。好，and if we look at the column of U matrix, it's turned out that the column of U matrix will be exactly those vector from U1, U2 to UN. So it is a n by n matrix. And if we want to reduce the data from n dimension down to k dimension, then we need to do is to take first k vector, then that give us u1 up to uk. Oh, sorry, this is k. Okay, this is a typo that n should be replaced by k. Okay, wait a second. Okay, so we will get an n by k matrix. So we call this column from U1 to UK. So the rest of the procedures, we are going to use the first K column of this matrix to get U1 to UK. Now the other thing we need to do is to take our original data X. Oh, here's K, sorry. Okay. Okay, we will take our original data X, which is an Rn, and we want to find a lower dimensional representation Z, which is Rk for this data. Then we take the first column, K columns of U matrix to construct this matrix, like we stick up U1, U2, and so on up to UK in a column. So this is going to be an n by k matrix. So we call this matrix U like U reduced matrix, which is a reduced version of a matrix U, and we are going to use this matrix to reduce the dimension of our data. And the way we are going to compute Z um, is it's equal to this U reduce matrix transpose times X, or we can take this transpose of this U matrix, then in this way, and um, then takes this matrix times X. So for the dimension, this matrix here is going to be K by N, and X here is N by 1. So the product will be uh, K by 1 matrix. And so Z is a k-dimensional vector, which is exactly what we want here, right? Uh, we we say that our goal is to transform the data x from Rn to the representation z, which is Rk. So here we didn't mention the meaning of I here. So what is I? I is the training example I, so we can write this as xi, and uh, we can here we can write zi. 就是我们透过 SVD 我们得到一个k dimensional 的这个 U reduce matrix， 然后我们就是主要用它来乘上我们某一笔 data x， 然后我们就可以得到转换后这个k 乘一的这样的矩阵，当做变成我们这个降维后的 x 的表示的方式。So in the PCA algorithm, we take n-dimensional feature and reduce them to a k-dimensional feature representation. And note that the number of k is a parameter of the PCA algorithm. Or you can say k is the number of principal component that we want to retain of our data. So to choose k, that is to choose the number of principal component, like some useful concept of our data. So what PCA tries to do is to try to minimize the average squared projection error. So it tried to minimize this quantity, which is the difference between the original data x and the projected version x approximate I. So it tried to minimize the square distance between x and its projection onto the lower dimensional surface. So that's the average squared project error. Also, we can define the total variation in the data to be average length squared of these example xi. So the total variance in the data is average of our training set of the length of each training example. So we can say it means that on average, how far are our example from the vector from just being 0, and how far on average are our training example from origin. So when we try to choose k, is to choose the smaller value so that the ratio between these is less than 0.01. So in other words, a pretty common way to think about the way we choosing k is we want the average square projection error that um, the average distance between x and its projection divided by the total variance of the data. That's how much the data varies, and we want this ratio to be less than 0.01, or you can say we want this ratio to be less than 1%. Okay, or some people may think about choosing K's rather than choosing K, but like choosing whether the ratio uh, is lower than uh, the defined value, like 0.01 or other values. So if we say we choose the ratio should be less than 0.01, it means that we use the PCA that make 99% of variance is retained. It also means that this quantity on the left is less than 0.01. And the number of 0.01 is the most people often use, but other common value is 0.05. It would be 5%, or we can say in this case we can say 95% of variance is retained. And if we choose the value as 0.1, it is 10%. So 90% of variance is retained. So this is some common range of values that we would choose.那这边只是很快的讲一下这个选择 K 的部分。怎么选择 K 呢？就是我们希望选一个 K，让这个average squared error projection 可以尽量最小，就是它的这个x 跟它的映射的值的之间的差是越小越好的。然后所以就是我们希望选择一个 K 具有这样的特性。然后选择 K 的一个方式还就是说，我们希望它的这个average square error project error 跟它的 total variance 的这个之间的比例可以小于0.01这样子的性质。然后如果说可以换个角度说，如果说这个比值小于0.01的话，就是可以说是小于1%，然后就再换句话说是保留了这个 data 的99% 的差异这样子。然后是代表说我做了这样的降维之后，它还是可以保留它蛮大部分的这个差异性。好，然后这边只是说有一些数字也是我们常常会用来作为这个目标，就是我们希望这个比值小于这个数值。Okay, so how do we implement the algorithm? Here's one algorithm we might use. So to choose the value of k, we may start off with k equals 1, then we run through PCA. And so the process is we compute uh, uh, compute z1, z2 up to zn, and we compute all of those x1 approximates and so on up to xn approximates, and then we check if 99% of variance is retained. Then uh, this is a good ch choice, and we will choose the value of k equals 1 as our uh, final target. But if the value isn't lower than 0.01, then we will try k equals 2, and then we again go on this process and check if the value is less than 0.01. Um, if unfortunately k equals 2 cannot satisfy um, this condition, then we will do this again. So we would try k equals 3, try k equals 4, and so on until we get like k equals 20. Then we may find it meets our requirement that we find 99% of data have these retained, and we use k equals 20 as our choice. But so this is one way to choose the smallest value of k to make sure that 99% of variance is retained. But uh, you know that if we start from k equals 1, 2, 3 until to satisfy this condition, this procedure seems very slow, and we don't want uh, the to go like k equal to 1 equals 1 to in uh, uh, in unknown numbers. So we are trying another way, like if we want to implement PCA, it's gives us a quantity that makes it much easier to compute these things faster. For example, when we use SVD to get the matrix U, S, and D, and uh, we we use uh, SVD on the covariance matrix sigma. It also gives us back the matrix S. The matrix S is going to be a square matrix. It is an n by n matrix, and it is diagonal. So the diagonal entries S11, S12, S22 to SNN are going to be the only non-zero element in this matrix, and everything. Wait a second. Everything here and here oh, will be 0. So only Z1, Z22 to Zn will be a non-zero element. So the value in these two areas uh, are going to be 0, and the quantity can be computed as 1 minus some from I equals 1 through k of SII divided by summation from I equal 1 through n of SII. So we can say that we take another view of how to explain if k equals 3. We are going to do is to compute the numerator of is sum from I equal to equals I through 3 of SII, and in this case we just compute S11, add S22 and S33 here. Okay, and it divides by S11 plus S22 until SNN. So what we can do is just to test is these less than or equal to 0.01, or we can test if the sum from I equals 1 through k SII divided by the sum from I equals 1 to through n SII, if these result is greater than or equal to 0.99. So to make sure that 99% of variance is retained. And so what we can do, just slowly increase the number of k, set k equals to 1, equals 2, and equals 3. And we just test this quantity to see what is the smallest value of k that ensure the 99% of variance is retained. So we only we can only call the SVD function, and it will give us the S matrix, or you can call eigenvalues, and we don't need to keep to call the SVD function again and again. We just code it once and we will get this S matrix. Then if we can just add the S11 to S KK. So if we set k equal to 3, then we just only to sum the first 3 elements. And if you set k equals 4, then we just compute the 4 component, like S11 add S22 add S33 add S44, and this result is the same, right? So we just simply compute the value of different k. So in this case, we will efficiently to choose the proper number of k to perform dimension reduction. 好，那这边就只是说我们这个选择 k 的部分，那如果是iteratively 去做就有点慢，那我们就可以透过 SVD 来得到这个 S 矩阵。我们只要去计算这个斜对角这个数值，如果选 k 等于3的话，我们只要加这前3个，然后除以这个斜对角所有数值的加总，来确保说还有没有符合我们的目标，那就会比较快来执行这件事情。好，那 但这边我们就没有很细去讲这整个这个背后的数学原理这样子。那总之这是PCA 的概念。好，然后后面我自己准备一些关于前面提到的这个 clustering 啊，还有dimensional reduction 的这个一些做法，然后让大家来看一下，说我们知道了这些之后，我们怎么来玩我们的这个 word embedding。好，那我们就来看看。好，那这边呢，就是我的范例是放了一个这个中文的资料，因为我们之前都讲到英文的资料，对不对？那中文的资料我们要怎么用来 train word to vector 呢？这边就是跟大家介绍的是，我是想要 train word to vec。那其实大家可以去试试看，比如说下载 Globe 的 algorithm 来那个的 code 来 train 看 word embedding。那这边我是用 word to vec，就是我们之前介绍的 C 包或是 skipgram。好，然后我这边用到的是中文的 corpus。那英文的话，它有个特性，就是每一个英文字中间它有一个空白嘛，所以我们基本上在 train 这个英文 corpus 的这个资料的时候呢，我们基本上不太需要对它做太多的处理。那当然你也可以做一些处理啊，比如说看是要你要都把它转成小写吗？可是这可能会有个问题是，也许有些大写是有特性。总之，英文资料相对比较不需要太多的 preprocessing，那可能就是看个人的需求去做对应的 preprocessing。但是中文的资料有个特点，就是我们的中文呢，是会一个我们讲小的 span 好了，然后可能你会用逗点来分隔，代表一个小小的停顿，然后呢，再来你可能会用句点当做这一句的结尾，那也可能是用惊叹号、用问号等等的。那所以这个问题就在于说，我们不知道中文的词是什么，就是我们通常是看到一整句话，所以当然首先就是我们要先去做断词。好，然后但是我这边很偷懒，我没有去做断词。那个断词的部分在蛮久之前，蛮之前的课有介绍过，就是可以用中研院所开发的断词的系统这样子。那总之有很多断词系统，然后只要去对中文的文本做断词之后，我们可以得到这个一个一个词。然后在这边我是用断好的这个《红楼梦》的文本，大家可以看到就是这是被断出来的一个词，然后这边有底线，后面是它的对应的词性这样子。那我今天这边的范例是想要 train 一个用《红楼梦》的这个小说的来 train 的 word embedding。然后我想要去看它，比如说 cluster 会得到什么样的结果，那降维会得到什么样的结果，然后那总之我们就是要先准备我们的 corpus 来 train word embedding，这边特别是word to vec 这样子。那我后面会用到的是一个叫做Jameson 的 package，那它是 Python 的这个 package，然后那它的特点呢是我们必须要把我们的文本再整理成像是很多个 list，然后每个 list 它是一句话，然后一句话它又把它断成是，就是它不是一个 string。假设说这是我们的第一句话，然后那它有3个 words 这样子，那它会是以一个list 来呈现，那这边就有好几句话，然后每一句话都是以 list 来呈现的。那总之我们是要先把我们的资料准备成这样，然后呢，接下来我们就可以用这个 Jameson 所写好的这个 function，它的 word to vec 来 train 这个 word embeddings。好，然后那这边就是有设对应一些参数，就是比如说是设定说我们要用什么样的资料来 train，那这边就是我们前面所整理好的这个资料这样子，就是 字串的那样的串列的那样的资料。然后你可以设定的 vector size 就是你的 word embedding 的大小是多少，比如说你要设300维的，你要设400维的，还是看你想要就是最后得到这个维度是多少的这个 word embeddings。然后这就是 window size， 就是我们之前有介绍到说，它的这个 context 要看多少个字。那就可以根据你自己的需求要看多少字，就设定这个 window size。然后这边这个是说因为文章可能字很多嘛，好，那有些字也许比较冷门之类，你不想要看那些频率较低的字，那你就可以设定这个数值来过滤一些频率较低的词。那这个也是根据自己的需求设定的。然后再来 SG 这个就是看你是 skitgram 还是 C 报。如果是 skitgram 的话，你就设1；你是要用要 train C 报 model 的话，那就是用0。然后再来就是要 train 多少个 epoch，然后 worker 就是看你的这个运算的设备有多少的 workers 可以来用。然后后面就是比如说negative example 要设多少个等等，就是这些都是可以自己设定的。好，然后总之我们这样一行就写完，就可以让他去来 train 这个 word embeddings， 然后我们就把这个 train 好的这个word embeddings 存下来。那之后只要存下来之后，我们任何时候要使用，就把它再 load 进来。然后那 Gensyn 它的这个 Word to Vec 有提供一些蛮好用的方法，比如说你可以找 given 某个 word， 然后你想要找最相似的前几名，然后那它就会对这个given 这个 word 去跟其他的 word 算它的 cosine similarity。然后那我们之前有提到 cosine similarity 就是介于0到1之间，那越接近1就表示说这两个字它是越相近的，语义越相近的。所以那它在这个方选中我们可以找到most similar 的前4个字，然后是跟比如说我想要测跟贾宝玉最相关的，然后就找出了这些词。那比如说找到第1名对象是曾宝玉，好像也还蛮合理的哈。然后其他就是相对就来说就是一些人名这样子。OK， 好，然后呢它还有一些这个 attribute 可以使用，比如说是想要看它的这个这个总共有多少个 word 的话，就可以用这个指令来看。然后你想要看对应就是每一个 vector 对到的是什么字的话呢，可以用这个 index to key 来看，说第一个它这个 matrix 的index 等于0的这个 row， 它是代表逗点这个字，其实是符号啦。然后再来是i 等于1的这个 index， 它的这个对应的 word 是了，这样子。好，那所以接下来再来看，如果说我们把这个刚刚 train 好这个《红楼梦》的 word embedding 来做 cluster 的话呢，要怎么做？那其实前面讲了好多有一个非常好用的这个 package， 就是scikit-learn， 它都帮我们包好了所有你想要你可能会用到的 machine learning 那些的这个model 什么等等的都可以在上面找得到。那就是我们直接用它写好这个 k-means 的演算法，然后来帮我们做这个 clustering。好，那这边有一些参数，比如说最重要的当然就是设定要多少个 cluster， 比如说我们先设2个好了，然后后面的 fit 这个里面的这个要放的就是我们的这个 word embedding。然后我这边写了很长，主要只是想要挑选那些就是字串长度是超过2的，就是我不想要看这些不太重要的字，就是只有单一一个字的，就相对来说比较不那么重要这样子。然后 它就经过这一行就可以开始 run 这个 clustering 的这个过程，然后等 run 好了之后呢，你想要知道你的每一笔 data 被分成哪个 cluster，那就可以用点 labels 这个 attribute 来看，然后就比如说这是属于一这个 cluster，然后第二笔 data 是属于第0的这个 cluster， 它们代表就是1、2笔的 data 是属于不同的 cluster。然后那后面就只是我们想要把它 print 出来说，第0这个 cluster 它有什么样的字，第这个1的这个 cluster 有什么样的字，但是呢，在这个例子好像就说不出个所以然来，就是好像两边都有人名，然后不太确定说这个 cluster 代表具有什么样的意义。好，那在这样情况下，我们也可以试试看，再做这个选择更大一点的 k 的值来看看。那比如说我这边先试5好了，然后在这边好像稍微就可以嘴炮个几句，那比如说好像0这个 cluster，有提到这个什么衣服相关的概念等等的。然后1的话好像是有一些称谓，像是什么老爷、老太太，然后2的话好像有些什么转折词吗？或者是一些连接词的感觉。然后3这个 cluster 就有开始有人名了。那4好像就是相对一些呃怎么讲，跟其他 cluster 又不太相关的一些字这样子。好，所以你可以看到这个我刚刚所陈述的这个过程，就是去解读说这个每个 cluster 有什么样的性质这样子。那基本上这个过程大概就是这样子。然后我们之前试过的是说，我想要去 cluster 那些动词，因为或者是说我们想去 cluster 一些物件，比如说它应该是属于衣服，还是它是属于其他物品，像是车子或者是什么，像是食物等等的，就是用这个方式来做 cluster，也就是当我们不知道说我们应该有哪些 category 的时候所使用到的这个方法。好，然后在后面是关于这个降维的部分，就是我们前面也有提到说，我们这个我们的 word embedding 维度很高，是300维，我们不知道它们这之间点跟点之间到底有什么样的这个物理意义这样子，那我们就可以用降维的这个方法来帮我们去解读我们的这个word vectors。那这边我们刚刚提到是用 PCA 嘛，那Scikit-learn 也帮我们都包好了，就不用自己写。好，那就直接用那个他所提供的 PCA。那这边设参数就是设说我想要把它降成2维的，然后我们就可以开始去让它的 PCA 的这个 algorithm。那大家可以看到，就是降维之后，就是变成我们总共有4888笔，然后这些资料都是2维的。最后就是做这个视觉化的部分。那视觉化的 package 的话，会推荐除了Matplotlib 以外呢，还有一个是这个 Seaborn， 我应该没有念错。就是这个也算是大家蛮常用到的一个 package 来做这个关于这个资料的这个视觉化的部分的这个分析。然后所以我们就把刚刚降维后的资料 load 进来，然后我们就可以用 Seaborn 所提供的这个他画 scatter 的这个方法，然后我们就把一些参数设定好，然后就可以这就是我们刚刚这个投影片的范例，就是这个是用《红楼梦》小说所劝出来这个 word vector，然后大家可以看到我有一些这个颜色点是前面就是我用 k-means 所得到的那些 label，然后可以看到就是他们有这个分群这个结果那你这时候你就可以再嘴炮一下，就是这是什么类啊，然后跟这一类很近啊什么的等等的。好，然后所以就是跟大家介绍，就是关于说以后你怎么分析你的这个 data 这样子。好，然后那这边有个缺点是 PCA 它可能在就做这个投射的时候会把点跟点压在一起，那是它是先天的问题，所以我在这边写，我会建议大家用 TSNE， 这个会是相较 PCA 再更好一点的方法。那其中最有名的例子就是大家不知道有没有听过这个很有名的一个例子是做手写数字辨识，然后那有人有试过用 TSNE， 它就是可以很有效把这个手写数字的那些不同的数字可以有效的分开，这样子就不会尽可能不会有重叠的情况，所以 TSNE 也是现在大家比较多选择使用来做 visualization 的一个方法。然后那在这边我是试用了这个《红楼梦》的小说来玩这个过程，大家可以看到这个。其实我的资料量不是很多，它这个句子数量偏少这样子。我们通常会喜欢用大概有上百万、千万的句子来 train word embedding 会比较好。所以这也有可能是因为资料量偏少的原因，所以我在这个要跟大家嘴炮这个 cluster 的性质的时候讲不太出来的原因。所以后面我有再跟大家建议说，或许你可以拿其他的word embedding 或是 sense embedding 来玩玩看。来看看这个cluster 后的结果啊，或者是 visualization 的结果。好，那这是我自己做的一些小实验，跟大家分享。那刚好告一个段落，不然我们就先休息10分钟，等一下我们再来讲下一个内容。我们等一下会讲，我新上传的这个投影片是logistic regression，那也就是代表会进入到supervised learning 的一些概念，然后是怎么用在 NLP 上面。好，那我们就先下课休息10分钟。 好，那我们再来上课吧。那在这节课的一开始，想要跟大家讲一下 Final Project 的报告的相关的事情。那我最后决定就是让大家用线上报告的方式。那我们一样就是透过这个 Google Meet 来让每一组在线上报告，然后每一组预计会有10分钟的报告的时间，然后会再留约2分钟的时间，让其他同学可以对报告的这个组别的同学提问。所以总共就是每组会有10分钟报告时间跟2分钟的 Q&A 的时间。然后我们会有2周让同学们报告，那分别是6月9号跟6月16号。那6月9号就有8组要报告，然后是第1组到第8组。那16号就是第9组到第16组这样子。那6月9号要报告这些组别，就请把投影片在6月8号的晚上12点之前上传投影片到这个连接，然后16号要报告的这些同学就请在6月15晚上12点之前把简报上传到这个连接。好，那有鉴于上次就是让同学们就是作业2前3名的同学报告遇到的问题，就是不能分享荧幕的这个问题，我后来又有在测试几遍，但很神奇的是，不管怎么测试都可以分享荧幕，那所以我们到时候再试试看。那如果还是有问题，就是当然就是我这边就是这个备用的方案，就是由我来帮大家播放简报这样子。好，那所以这是关于Final Project 的这个 presentation 的一些时间上面的规划。好，然后我们预计也会让大家填互评表，就是每一个人、每一个同学可以选一组，就是你觉得他是除了自己以外，这个表现最棒的那一组，然后最后我们统计结果，这个前3名的组别就可以有特别的 bonus 可以加分这样子。OK， 好，那这是关于 Final Project Presentation 的说明。OK， 那不知道大家有没有什么问题？如果有关于 Final Project Presentation 的问题，可以在即时讯息跟我说，或者是你后来才想到的话也没关系，你就再寄信给我或是助教。OK， 好，那接下来要跟大家介绍，从 logistic regression 介绍开始，然后我们会用一个例子，就是 sentiment analysis，然后来介绍这个 supervised learning in NLP 的一些概念。那刚好我们的这个之后的作业也会跟这个有相关，那希望可以给大家一些基本的概念。让大家可以就是在写作业的时候比较顺利。好 So in the following slide, I will talk about classification problem, uh, where we want to we will use logistic regression to perform the classification task. So logistic regression is one of the most popular uh, learning algorithms in supervised learning. But before introducing logistic regression algorithm, we are going to learn about supervised machine learning. In supervised machine learning, we have input feature X and a set of label Now, to make sure we are getting the most accurate prediction based on our data, our goal is to minimize our error rate or cost as much as possible. So to do this, we have to run the prediction function to output the label y hat. So where the prediction function takes the parameter data to map our features. Now the best mapping from features to uh, labels is achieved when the difference between the expected value um, y and the predicted value y hat is minimized. And it is measured by the cost function that comparing how closely that the output y and y hat and your label y, then we can update our parameter to repeat the whole process until our cost our cost is minimized. 好，所以简单来说，就是我们需要在 supervised learning，我们需要有data，把它它是以向量方式来表示，所以我们也会称它叫 feature，然后以及它对应的 labels。那这 label 是什么呢？等一下会提到。那总之，我们就根据这样的特性有一个所谓的 prediction function。那所谓的 prediction function，我们当然也可以用，比如说 logistic regression 之类的这个 algorithm 来得到根据这个 input feature 得到一个 output，然后我们用这个计算这个 output 跟 label 之间的这个差距，来衡量说我们要怎么去更新我们的 models，然后去更新我们的 model 之后，就是一直这个重复的过程，希望它这个我们 output 就是 predict output 跟我们的实际的 ground truth 的这个差距越来越小。那直到某个程度之后，我们可以停止这个过程，就代表说我们已经 train 好了一个 prediction function。Okay. So let's see some example of classification problem in supervised learning, especially in the field of natural language processing. So one of example in natural language processing is email spam classification that focus on identifying whether email is a spam. And another example would be classifying users' opinion, like the reviews of product that are posted online. And it would be like positive sentiment or negative sentiment. So in this problem, um, the variable that we are trying to predict is a variable y that we can think of as taking on two value, either zero or one. So you can say either span or not span, either positive sentiment or negative sentiments comment. Okay. And another name of for the class we denote with zero is you can say the negative class, like not spent, or uh, uh, when y equals one. Another name for this class is that we denote with one is the positive class. So for example, zero is not spent and one is defined divided as spent. So for now, we are going to start with classification problem with just two classes like zero and one. And you may be wondering how to perform multi-class problem. Here is called binary classification problem because we only have two values, so it's called binary classification. And another classification problem is called multi-class problem because in multi-class classification problem, we have more than two values to predict. So maybe we have three value like 0, 1, 2. So in this case, simply y of multi classification problem may take like four values 0, 1, 2, 3, and it is called multi-class classification, but we will start from binary classification problem, and then uh, uh, we will uh, introduce the concept of multi-class classification problem and how to use like logistic regression algorithm on multi-class classification problem。好，那就是这边如果是这种 supervised learning 的这种分类问题呢，那我们就会有定义不同的类别，比如说在 NLP 我们想要分辨是这封 email 是不是垃圾邮件，或是这一则评论它是对这个某个议题是正面还是负面的，那我们就定义两个 label， 一个是 negative， 一个是 positive， 然后我们就是第一步准备我们的这个 label 的过程，然后那所以我们会先从这个 binary 的，就是只有这两个类别的这个分类问题开始谈起，然后之后再来看 multi-class 有多个类别的情况是怎么做的。Okay, so to get started building a logistic regression classifier that is capable of predicting sentiment of a text like a tweet. Okay, we will first process the raw tweets in our training set and extract useful features. Then we will train our logistic regression model while minimizing the cost. And finally, we will be able to make our predictions. So this is the step that requires for us to classify a text. And here is a tweet with the content is I am happy. So given this tweet, we should classify it to either be a positive sentiment or it's expressed like negative sentiments. So the first we have to do is to extract features. Then we have to train our model. And here we start from logistic regression model. So let's take a look at the supervised machine learning classification text of sentiment analysis. In this example, we have the tweets, I'm happy, and the objective in this tag is to predict whether the tweet has a positive or a negative sentiment. And you will conduct this by starting with the training set, where tweets with a corresponding label like positive sentiment, and the tweets with the negative sentiment have the label of zeros. So the positive sentiment have a label of 1. And for this text, we will use logistic regression classifier, which assign its observation to these two distinct class, like a positive sentiment, or you can say the label of 1, or the negative sentiment, which is a label of 0. Okay, 好，在这边我们等一下会介绍 sentiment analysis。那什么是 sentiment analysis 呢？就是我们会给定一个文本，不管它是一篇文章或是一个句子，比如说来自一则 tweet，那这样子的这个 文字的资料，我们想去分析说这个文章里面它所表达的这个情绪是正面的还是负面的，那这样就是 sentiment analysis 情绪的分析。那有一些过程，首先就是我们要先把文字的资料转成 features。那features 通常就是会以数值来表示。那文字怎么转数值呢？其实大家都已经学会了，就是比如说我们可以用 one-hot encoding，那你当然也可以用 TF-IDF 的 value 去建立它对应的vector，然后你当然也可以用 word embedding。那后面我们会再介绍其他的方法，比如说用很有名的，比如说BERT model 来得到sentence embedding 或者是 document embeddings。那总之我们就是用任何其中一种方法把文字的这种 symbol 的资料转成这个 vector，然后我们就丢到了我们的 machine learning 的 model， 比如说 logistic regression 的 model， 然后它的目标就是要去 minimize 它的 prediction 跟它的 ground truth。那所谓的ground truth 就是它的这个情绪的标记，然后prediction 当然就是它会预测它是正面还是负面的这个sentiment。OK。So let's start talking about logistic regression. Here we will start from the hypothesis representation. That is what is the function we are going to use to represent our hypothesis when we have a classification problem. You can say that we would like our classifier to output the value between 0 and 1, right? We have the two values of label as 0 and 1, so of course we would like our classifier to output value that are between 0 and 1. So we would like to come up with a hypothesis that satisfy this property. So it means that we hope that the prediction are between 0 and 1. So when we are using the logistic regression, the hypothesis is g of z. Oh, okay, so this is the function called sigmoid function, and someone called logistic function. So here g of z, z is a real number, is equal to 1 1 over 1 plus e to negative z. So okay, so he did this sigmoid function, and by the way, the term sigmoid function and logistic function are basically synonymous, and it means the same thing. So the two terms are uh, either can be used to refer to this function g. And if we take this equation, and it is an alternative way to write the form of our hypothesis. So we can plot it on the figure here, the sigmoid function, and it start off near 0, then it rise until it cross 0.5, and then it flatten out again like this. So so this is the sigmoid function looks like. And you notice that the sigmoid function it's start at uh, from 0 to 1, and as this axis, the horizontal axis z, as z goes to minus infinity, approach 0, and as g of z approach infinity, here approach 1. And so because g of z are the value of g of z are between 0 and 1, we will have the output must be between 0 and 1. So here we can say the output of this function um, is the probability that if the probability upper than 0.5, we will say the logistic regression model predict as the number the class 1, and if the probability is lower than 0.5, then we can say that the model predict the input as the class 2. So here is the logistic regression, the sigmoid function. Its input the uh, feature vector and times the corresponding weight. And then it's add a bias, then input the sigmoid function, then it will output the value between 0 to 1. Then we map to the concept of probability to say the meaning of the prediction. So given this hypothesis representation, what we need to do is to fit the parameter uh, uh, to our data. So given the training set, we need to pick the value for the parameters, and this hypothesis will then lead us to make the prediction. Okay, so let's talk about the learning algorithm for fitting the parameter and the interpretation of this model. 好，这边很快跟大家讲一下，就是我们现在要做的是要分类，分两类这样子，然后大家可以视为是我们要借用一个 sigmoid 的方选，这个 sigmoid 方选它有个特点就是它会吃进去这个 z 的 input。之后，它会把这个值 map 到介于0到1之间的数值，那它是可以当做这个几率的感觉。如果这个几率的值大于0.5，我们就把它视为是 model 分类成第一类，然后否则的话就是分类为第二类。那这边的 input 就是我们的 feature x，那它们都会乘上对应的 weight w，然后再最后加总起来，再加上一个 bias。好，那所以这边的这个function就是换句话说是受到这个 w 跟 b 来控制来得到最后的 output， 然后那这个意涵就是根据这个 x 我们去预测它属于C1 的几率是多少这样子。好。So let's interpret the output of our hypothesis, h of x. Visually, the sigmoid function has this form, and it approaches 0 as the dot product of theta transpose x over here approach minus infinity, and 1 is approach to infinity. So for classification, a threshold is needed. In general, we will set to be 0.5, and this value corresponds to the dot product between theta transpose and x equal to 0. So whenever the dot product is greater or equal than 0, the prediction is positive, and whether dot product is less than 0, is the prediction is negative. And uh, in the following slide, uh, we want to talk about the hypothesis representation of logistic regression, and we have introduced that uh, we we want to we want to train a model to predict the uh, value given the input x. So this process, we can also say we want to find the boundary. So it's called the decision boundary, and this will give us a better sense of what the logistic regression hypothesis function is computing. So we said that hypothesis function is computing is represented as h of x equals g of uh, theta transpose times x, where g is the function called sigmoid function, and it slowly increased from 0 to 1. Now, um, uh, this hypothesis will make prediction that y is equal 1 uh, when it might uh, make a prediction um, that y is equal to 0, and understand better what hypothesis function look like. We have more than one feature. So this hypothesis computing, outputting estimate of the property that y is equal to 1 given the input x and the parameter theta. So suppose us have a training set like this, and suppose a hypothesis uh, is h of x equals g of uh, uh, theta 0 plus uh, theta 1 times x plus x1 plus theta 2 times x2. We uh, and we end up choosing the value of the parameter like 0 theta 0 equals minus 3, theta 1 equals 1, theta 2 equals 1. But this means that my parameter vector is going to be theta equals minus 3, 1, 1. So given this choice of our hypothesis parameters, um, let's try to figure out where the hypothesis would end up predicting 1 equals um, predicting y equal 1. If uh, it would end up predicting y equals 0. So using this formula, um, we know that y equals 1 is uh, more likely that the probability that y equals 1 is greater or equal to 0.5. And this formula is minus 3 plus x1 plus x2. So the theta transpose x when theta is equal to this value uh, of the parameter that we just choose. So for example, uh, if the equation that the example will make this equation greater greater or equal to 0, our hypothesis will think that y equal to 1. So the prediction of y is equal to 1, and we can also take uh, minus 3 from here to here, then we rewrite this function as x1 plus x2 is greater or equal to 3. So we find that this hypothesis would predict y equal to 1 whenever x1 plus x2 is greater or equal to 3. So to see what the means on this figure, if we write down these equations, and this define the equation of the line, and we and I draw here, for example, like this green line. So um, so you can say that uh, these right half things, uh, that everything to the up and everything to the upper right portion of this line, uh, it's belong to uh, uh, it's sorry, these points are regarded as being predicted as one equal y equal to equals 1, and in these regions it's um, we call this is y equals 0 regions. So in other words, region on uh, the left region is our hypothesis will predict y equals 0. So this line is called decision boundary, and uh, specifically, this line is x1 plus x2 um, equals 3. So to be clear, the decision boundary is a property of the hypothesis, including the parameter theta 0, theta 1, theta 2. Okay, so in the decision boundary and the region, we predict y equals 1 or y equals 0 is a property of these hypotheses, not the data set. 好，那所以简单来说，这个训练这个 logistic regression 的过程，它就是我们根据给定的资料来 train 这个我们的parameter。那这边是这个 theta 0、theta 1、theta 2，然后把它换个方式来看的话，你可以想象，假设在二维空间上，我们要就是找一条线，可以来分隔属于不同类别的资料。好，然后那我们就是目标找出一条完美的线，就是一条好的线，可以很好的分开这两类资料。Okay, so if our example is more complicated, for example, like this, so do we how can we get logistic regression to fit the sort of data? And the answer is we could add uh, extra or higher order polynomial terms to the features. So let's say we have the hypothesis look like this, where we add two extract features, so that we have 5 parameters, and like theta 0 through theta 4. So after training, the value for the parameter theta through theta 0 through theta 4 are chosen, and it end up like it choose uh, the, the value of theta 0 equals -1, and 0 and theta 1 and theta 2 uh, equals 0, and theta 3 and theta 4 equals 1. So it means that our hypothesis will predict y equals 1 if uh, minus 1 plus x uh, x super 2 sub 1 plus x super 2 sub 2 uh, greater or equal to 0. And this is whatever theta transpose times our theta uh, trans transfers. So so the feature is greater or equal to 0. And if we take the value minus 1 to here, and we can say the hypothesis will predict that y equals 1 whenever x super 2 sub 1 plus x super 2 sub 2 greater or equal to 1. And we can add more complicated feet add more complicated uh, make our equation more complicated, like we add more features into these equations, then we can have a more complicated uh, model and end up having a more complex decision boundaries. So if the higher uh, polynomial features, we can have a very complex decision boundary to fit your data. So uh, in the following class, in the following slide, we want to talk about how to fit the parameter and end up using training data to find the parameter. 好，那这边只是说，如果我们的资料复杂一点，当然我们可以加更多的参数来让我们的这个式子更复杂。你可以画出更复杂的的线条来当做这个你的 decision boundary。OK。So we will talk about how to fit the parameter of theta for logistic regression, and here we define the cost function to fit the parameters. And here is a supervised learning problem of fitting logistic regression model. So we have a training set of n, m training example. So here we represent, like we have the data x1 and the corresponding label y1, and the second data is x2 and its corresponding label is y2. So for each x, we can represent as a feature or vector space, uh, uh, like um, feature like in natural language processing, we can represent as the word vectors or one-hot encodings, and uh, uh, we can set the value of y equals to either uh, 0, 0 or 1. So this is the hypothesis, and the parameter of hypothesis is theta over there, and the equation that we have to talk about is given this training set. So how do we fit the parameter of theta? So if our correct answer y is 0, then the cost function uh, will be 0 if our hypothesis function also output 0. So if our hypothesis approach 1, then the cost function will approach infinity. On the other hand, if our correct answer y is 1, and then the cost function will be 0 if our hypothesis function output 1. If our hypothesis approach 0, then the cost function will approach infinity. 好，那这边就只是讲一下怎么准备我们的这个资料。首先从 training data，然后来讲到 cost function 的概念。那总之我们会有两类，0跟1。然后如果我们的 output，我们的 model 的 output 是0，然后我们答案也是0的话，那这个我们的这个 hypothesis function 的 output 也会是0，否则就会是是非常大的数值。那反之亦然。OK。好，OK，here's the cost function for logistic regression, and the overall cost function is 1 over m times the sum over the training set of the cost, making difference prediction on the different example of labels y, I, and this is the cause of single example that we mentioned earlier, and just want to remind that for the classification problem in our data set, it's um, the training set y is always equal to 0 or 1, and because y is either 0 or 1, we will be able to um, come up with a simpler way to write the cost function like this. We can write the cost function on two separate line with two separate case, like if y equals 1 and y equals 0, but we can take these two lines to compress them into one equation, and this would make it more understandable to write out the cost function and derive gradient descent. So in this equation, we can say the cost of h of x, y, um, we can write like uh, um, minus y times log uh, h of x minus 1 minus y times log 1 minus h of x. And these equations, uh, here we can say that if y equals 1, then this equation, the cost is here like the value is 1 minus 1, so this value is equals to 0. Then we can write the cost is uh, if y equals to 1, then the function, the equation is minus log log of h of x. Okay, so so if y equals 0, means in this case, so then we write the cost function, the y is y equals 0, so this term is equals this term equals to 0, then 1 minus 0, so this value is 1. Then we get the equation is minus log of 1 minus h of x. So here we we can see that this definition for the cause is just a more compact way of thinking both this expression that the case one equals y equals 1 and y equals 0, and writing them in more convenient form, just one line. So okay, so again, if our correct prediction is 0, then the cos function will be 0. If uh, the prediction and the ground truth is different, then the cos will approach infinity. Okay, so we can write all our cos function for logistic regression as follows, like this 1 over m of sum over, sorry, start from here. Okay, we can write the cos function as 1 over m of sum of these cos function, and based on the definition of the cos, we just put minus sign outside. So here this is our equation of the cos function. So given this cos function, how can we fit the parameters? The answer is uh, what we are going to do is to try to find the parameter theta that minimize the cos function j of theta. So if we try to minimize this, this would give us a set of parameters theta. Then if we given a new example with some set of feature, we can take this theta to feed our training set and output our prediction as this. So the output of our hypothesis is can be uh, interpreted as the property that y is equal to 1, and given the input x and the parameter theta. So we can think this as estimating the probability that y equals 1, and so um, the the process is to minimize j of theta function, so we can fit the parameter to our training set. 好，总结来说就是我们的 cos function 可以写成像这样，因为我们是两个 case y 等于1跟 y 等于0，然后在我们把它写成这样的式子之后呢，当你代入 y 等于1的时候，会对应到这个 function，因为我们如果把 y 带进去，大家可以知道就是这一项消掉，然后或是 y 等于0的话，这一项消掉，就是等于说我们用这两个式子去算对应它的 y 是多少的时候的 cost， 然后所以主要的目标是我们用这个 cost function 来根据我们的目前这个 function 的 output 跟给定的 ground truth 去算它的 cost， 然后我们想要去 minimize 这个 cost， 因为 minimize 这个 cost 就代表说这个我们是希望我们预测出来的这个 probability 它是可以越接近这个 ground truth。那我们 ground truth 是0跟1嘛，然后我们的 output 是像是 probability 是它可能是0.5、0.6。那我们希望就是我们如果它的这笔 data 的 ground truth 是1，那它的 output 的 probability 就越接近1是越好的。好，然后那后面的话就是几页是比较快速带大家看过这个 logistic regression， 但后面的话还有在准备一个例子是关于怎么用logistic regression 来做这个 sentiment analysis， 然后接下来就是会再进到 neural network 的部分，然后呃在下一周可能就可以讲到像是 RNN， 然后再更进阶的 transformer。OK， 那 看到现在时间也差不多要让大家下课休息了，那我们今天就先讲到这边，那大家可以下课休息了。